Hi there, this is Estelle Trengove. I've been asked by someone in the LN2017 class to do an example of superposition with a dependent source. So here it is. I'm using the circuit from example 4.7 in the Alexander and Sadiku textbook. In the textbook, they find Vx using source transformation, and we're going to find Vx using superposition. The important thing to remember is that when there's a dependent source in a circuit and you use superposition, then you leave dependent source in the circuit. First, let's omit the 18-volt source. So we're going to find the effect of the 6-volt source only. And then our circuit looks like this. We're going to call this quantity Vx dashed because it's the effect of the 6-volt source only. You'll see we've left the dependent source in, so this is now 0.25 Vx dashed. And then you'll also see that over here we've omitted the 18-volt source by short-circuiting it. So we've got the 18-volt short-circuited. And now if we look at the circuit, we can see that we can probably simplify it a bit by transforming this 6-volt source with the 2 ohm resistor in series into a current source with a resistor in parallel. So the current source is going to be the voltage of 6 volts divided by the resistance of 2 ohm. So it'll be a 3 amp current source in parallel with a 2 ohm resistor. And then we've still got the original 2 ohm resistor from our circuit. And we've got Vx dashed here. And we've still got that current source. Of 0.25 Vx dashed, and we've still got the 4 ohm resistor. Now, if you look carefully, you'll see that this is one expanded node. So this is all one node. And then you'll also see that this is one expanded node. So this is all one node because there are no circuit elements connected in between. And then you see we can draw this circuit like this. So we've got the 3 amp source. And then we've got the two ohm resistors in parallel with each other. So that's 1 ohm, and this is still Vx dashed. And we've got the current source, the dependent current source, which has a current of 0.25 Vx dashed. And we have the 4 ohm resistor. And now you can see that the 4 ohm and the 1 ohm resistors are in parallel, so we can redraw this circuit like this. We've still got that 3 amp source. And we've got the 4 ohms in parallel with 1 ohm, which gives us 0.8 ohms. And we still have the dependent current source. of 0.25 Vx dashed. So you see, circuit analysis is like magic, because now if we look at the top node over here, let's call this current I1. Then by Kirchhoff's current law, we've got I1 flowing out of that node, and that must be equal to 3 amps plus 0.25 Vx dashed. But we also know by Ohm's law, Vx dashed is equal to 0.8 ohms times I1. So if we put that into that equation, we get I1 is equal to 3 amps plus 0.25 times 0.8 I1. And if we work that out, it gives us I1 equal to 3.75 amps, and therefore Vx dashed is equal to 3 volts. So now we've worked out that the contribution that the 6-volt source makes to Vx is Vx dashed equal to 3 volts. And now we have to work out the contribution that the 18-volt source makes. So over here, we've short-circuited the 6-volt source, which means that the two 2-ohm resistors are in parallel. So we can redraw the circuit like this. So the two 2-ohm resistors in parallel become a 1-ohm resistor, and the voltage here is still Vx double dashed. And let's, for the purposes of analysis, call the current flowing here I2, and we'll call this current I3, and let's call this node VA and this node VB. At node VA, by Kirchhoff's current law, we have flowing into the node the dependent source, which is 0.25 Vx double dashed. And we've also got flowing into the node I3, and flowing out of the node we have I2. So 0.25 Vx double dashed plus I3 must be equal to I2. But we can see that by Ohm's law, I2 is equal to Vx double dashed divided by 1 ohm, which is equal to Vx double dashed. And so if we put this into that equation, then we get 0.25 Vx double dashed plus I3 is equal to Vx double dashed, and so therefore I3 is equal to 0.75 Vx double dashed. Now let's call the voltage here Vy. And so you can see that by Ohm's law, Vy is equal to 4 ohms times I3. And so from the equation above, it's equal to 4 ohms times 0.75 Vx double dashed. And so therefore Vy is equal to 3 Vx double dashed. And now we're going to go around the big loop in this circuit and apply Kirchhoff's voltage law. So by Kirchhoff's voltage law, going around the big loop over there, we've got minus 18 volts plus Vy plus Vx double dashed is equal to 0. So remember Vy is 3 Vx double dashed, so 3 Vx double dashed plus Vx double dashed is equal to 18 volts. And therefore Vx double dashed is equal to 4.5 volts. And so finally, to find Vx, we know that Vx, we've got to add all the parts that we found through superposition. So Vx is equal to Vx dashed plus Vx double dashed. And remember, we said that Vx dashed was equal to 3 volts. And Vx double dashed is equal to 4.5 volts. And so Vx is equal to 7.5 volts. And that's the end of this recording.